Our next family of functions we need to know how to do calculus with, the inverse trig functions. So let's derive them. Start with inverse sine x, and obviously at this stage we don't know how to do it, but we do know how to differentiate a sine function. So if I make x the subject and make it x equals sine y, and instead of finding dy dx, I'll find dx dy. Differentiate sine, we get cosine. So I now have dx dy, turn it upside down, I've got dy dx. The only difference now is it's the y value I'm substituting in instead of the x value. Well, that can kind of be inconvenient, especially when we're doing things with respect to x. So let's get x back in there. How do we do that? Well, we know x is sine y. How do I turn cosine into sine? I make it the square root of cos squared. Cos squared then becomes 1 minus sine squared, and now I can get the x back in there. So 1 over the square root of 1 minus x squared. Let's now do inverse cos, same way. We'll make x the subject. Let's find dx to y. Cos goes to minus sine. Turn it upside down, but how do I get x back in there? Now I've got to turn sine into cos, but I'll use the same trig identity. Square root of sine squared gives me 1 minus cos squared, 1 minus cos squared. Well, cos is x, so we get 1 minus x squared. We see very similar answers. It's just the inverse cos one's negative and the inverse sine one's positive. And when you think about that, think about your actual curves, it does make sense because your inverse cos curve and your inverse sine curve are very similar curves. One's like a reflection of the other and shifted a bit, but they're basically the same curve, just moved around a bit. Let's try inverse tan then. X equals tan y. Now when we differentiated tan, it went to sec squared. So dy dx is 1 on sec squared. How do I get x back in there? Now x is tan. How do I turn sec squared into tan? Again, trig identity. We know 1 plus tan squared is sec squared. So this one doesn't have the square root because we had sec squared rather than just sec. So we get 1 over 1 plus x squared. So that gives us the derivatives of the very basic inverse trig functions. So to generalize that, if it is a linear function, you can go 1 over the square root of a squared minus x squared. Inverse cos becomes minus 1 over the square root of a squared minus x squared. And the one that's a little bit different is inverse tan. It doesn't have 1 on the top. It has a on a squared plus x squared. And I've got to be honest, I don't usually do them that way. I do it this way because I just think it's easier. Inverse sine of function x, so that handles every function. It's the derivative over the square root of 1 minus the function squared. Inverse cos minus the derivative over the square root of 1 minus the function squared. And inverse tan becomes the derivative over 1 plus function x squared. I kind of prefer that one because it's got the derivative on the top of all of them, so you can see how with the other one you could make an easy mistake by not putting the a on the top. That's not to say those first three aren't useful for very simple functions, and we'll do some examples. So if we had inverse sine of 5x, here I would definitely use the second one. So I would go, well, that's the derivative, 5, over the square root of 1 minus the function squared. Square 5x, you get 25x squared. There's the answer. Inverse cos of e to the power of x, okay? Inverse cos goes minus the derivative. So we have minus e to the power of x over the square root of 1 minus the function squared. So square e to the x, we get e to the 2x. Here, I guess, is where that first formula becomes useful, because it's in the form of x over a. It's probably the only time I use it, right? So it's in the form x over a, so therefore the derivative is 1 over the square root of a squared minus x squared. You see, I could still have done it the other way, but just a little bit more work, because I would have said derivative, a third, over the square root of 1 minus the function squared, so 1 minus x squared on 9, but now I've got fraction on fraction, so multiply top and bottom by 3 effectively, and we get 1 on the square root of 9 minus x squared. So okay, when I do have that situation, that unique situation of x on a, yeah, all right, I'll use those first ones. But other than that, I tend to go with derivative over whatever. E to the power of the inverse cos of x. All right, it's an exponential function. So we differentiate the power. The power is an inverse cos function. Differentiate inverse cos of x, I get minus 1 on the square root of 1 minus x squared, but then we multiply that by e to the power, and the power does not change. So inverse cos of x, I don't like it like that. I'm going to write it all as one fraction. Minus e to the power of inverse cos x over the square root of 1 minus x squared. Let's do some anarchy. Can't do calculus without anarchy, can we? All right, bring down the power. 3, lower the power. 2, diff the inside. Differentiate inverse tan x. We get 1 on 1 plus x squared. Putting that all together, there's our answer. By the way, with inverse trig, remember, don't bring the power in and write it as negative 2. That negative 1 is not meaning the power of negative 1. So we write it as inverse tan of x squared. Oh, bit of a product rule. Write down the first, x squared. Diff the second. The second is an inverse tan function. So we go derivative. Derivative of x cubed is 3x squared. Over 1 plus the function squared. Square x cubed, we get x to the 6. Plus, write down the second, inverse tan of x cubed. Diff the first. Differentiate x squared, we get 2x. Tidying that one all up. 3x to the 4 plus over 1 plus x to the power of 6 plus 2x. Inverse tan of x cubed. Let's have a look at an old Hsc question, 2018. I like this question because it points out something nice. Function x is the inverse sine of x plus the inverse cos of x. Show that the derivative is equal to 0. Differentiate inverse sine, I get 1 over the square root of 1 minus x squared. Differentiate inverse cos, I get minus 1 over the square root of 1 minus x squared. So yes, indeed, that derivative is 0. Hence or otherwise. So you've got another way to do it. You feel free to do it. Prove the inverse sine of x plus the inverse cos of x is always pi on 2. You see, what they're getting at here is the derivative is 0. So if the derivative is 0, you must have just differentiated a constant. Because you differentiate a constant, you get 0. You are being asked to prove that inverse sine x plus inverse cos x is a constant. Well, if we just differentiated inverse sine x plus inverse cos x and got 0, because it is continuous over the domain, more about that in a second, but because it is continuous, then we know that's going to be constant. What is the constant? Substitute in 0. Well, you can substitute any number you like in the domain, really. Substitute it in and you can work out what the constant is. So we got pi on 2. So yes, that is true. Part C, all right, go and sketch the curve then. Now, the mistake that would be made here is to simply draw the line y equals pi on 2. But that's not the line. Well, it's not the line, but it is the interval. Because the domain of this is going to be minus 1 and 1, because the domain of inverse sine of x is in between minus 1 and 1. The domain of inverse cos of x is in between minus 1 and 1. So this new function that we got here still has to satisfy the domain. You can't all of a sudden magically substitute in 2, for instance. It's not going to work. So yes, it is the line y equals pi on 2, but just not the whole line. It's still got to sit in the domain. But it is, you will see, continuous over that domain. So why do I mention that? Because now I'm going to do a very similar question, but vary it a little bit. Function x is inverse tan of x plus inverse tan of 1 on x. Show that the derivative is equal to 0. So it's looking like the same sort of question. Differentiate inverse tan x, we get 1 on 1 plus x squared. Differentiate inverse tan of 1 on x. The derivative of 1 on x is minus 1 on x squared, so that goes on top. Over 1 plus the function squared. So 1 plus 1 on x squared. Ooh, fraction on fraction, don't like that. Let's multiply everything in that second fraction by x squared. And we get minus 1 on x squared plus 1. Oh yes, they add together to give 0. So it's looking like the same question. I'll just go straight to sketch. You see, the difference here is this one is discontinuous at x equals 0 because I can't sub 0 into that. 1 over 0 doesn't exist. So it's not continuous, this graph. So what does that do? We have to test either side of the discontinuity to see what this constant value is going to be. So right, when x equals 1, it's pi on 2, very similar to the last question we looked at. But if I go on the other side of the discontinuity, so let's pick x equals -1, we actually get negative pi on 2. So when I draw this one, sure enough, there it is on the right-hand side, but on the left-hand side, it will be minus pi on 2, and there's a discontinuity at x equals 0. Now, the domain other than x equals 0, the domain is going to be all real x, because if you recall our inverse tan function, its domain is all real x. That is what that one would look like. So what am I getting from this, especially when we're dealing with these inverse function type things, is if there is a discontinuity and you're trying to work out what that constant is, you check either side of the discontinuity to see if that value changes. That brings us more recent. The 2020 Extension 1 paper, so the first of the new course. And this is what they were presented with. Function x was the tan of the inverse cos of x, and g of x is the square root of 1 minus x squared on x. They gave us the graph of gx, which saves us thinking about what it is, which was nice of them. Show that the derivative of that first function is the same as the derivative of the second function. Well, we'll just differentiate both of them. So tan inverse cos of x. We're differentiating a tan function. Tan goes to sec squared. The angle doesn't change, so it's still the inverse cos of x, but it will be multiplied by the derivative of the inverse cos of x. The derivative of the inverse cos of x is minus 1 on the square root of 1 minus x squared. Okay, let's take this a bit further. Sec is the reciprocal of cos, so I've moved that sec squared to the bottom of the fraction and made it cos squared. So I now have minus 1 cos squared, the inverse cos of x, the square root of 1 minus x squared. Now, why do that? Because I've now got the cos of the inverse cos of x. They'll cancel. So that just becomes x squared on the bottom. And I might just stop with that one there. Let's now see what happens with the second function. We're going to have to use a quotient rule. Square the bottom, write down the bottom, diff the top. So the top ends up being minus x on the square root of 1 minus x squared, minus, write down the top, diff the bottom. Can we make these the same thing? Yeah, well, let's push the square root of 1 minus x squared into the denominator, which means that second square root of 1 minus x squared just becomes 1 minus x squared, but it's minus all that, hence minus 1 plus x squared. Minus x squared plus x squared minus 1. Yeah. We've ended up with the same thing. Ooh, very tricky. You can see lots of places to make silly mistakes in that one. All right, but we've done what they want us to do. They are indeed equal. Using part 1 or otherwise, show that the functions are actually the same. Now, it's not enough to simply say, well, their derivatives are the same, therefore the original function may have been the same. Not necessarily true, because they might have a different constant or something like that. Now, instead of playing with the derivative equals the derivative, I've moved everything to one side. Why? Because now, when I integrate this, I know I'm getting a constant. Because I'm saying this derivative of this thing is equal to 0. So the integral of f dash x minus g dash x must be a constant number. I'm hoping that constant number will end up being 0. See, because if that constant is 0, you see what happens. If I integrate f dash x, I'll get function x. If I integrate g dash x, I get g of x. And we're saying the difference between the two is a constant. Well, if that difference between is 0, then they are in fact the same function. Well, let's substitute in a value. But, hang on, let's go back to the original functions. If you look at the functions, and there's the graph just to help us, there is a discontinuity at x equals 0. So we need to check either side of the discontinuity. So you can see there's lots of places in this question to make these silly little mistakes. I'll pick a number bigger than 0. So I substitute in 1. The tan of the inverse cos of 1 ends up being tan 0 is equal to 0. Excellent. The constant is 0. But now let's check the other side. When I sub in minus 1, I get tan pi is equal to 0, but tan of pi is 0 as well. So yes, the constant is 0 on both sides of the discontinuity. Thus, function x does equal g of x. That shall do us.